I'd like to welcome you to the Thesis Defense Christmas office. I won't paraphrase the title because it's on the screen there, but Chris will give a presentation to start out this defense. It's the open part of the presentation, and at the end of his presentation, anybody who has questions can ask them. And then at the completion of the questions, we'll close our doors, all of you will exit, and then it'll be the committee and Chris talking about his thesis. So Chris, you can start. Before you start, I do want to define the committee. The committee consists of myself, I'm the chair, Dr. Larry Carey, and then Dr. Tim Coleman, who is on the road, but he's listening in and following along on his laptop, but he's not driving. I have him on speakerphone there, so he should be able to hear everything that we're saying. Can you hear me, Tim?
I hear you side by side.
Okay, good. So let's start.
Thank you everyone for coming today. I really appreciate your presence and encouragement throughout this time. We're going to talk a little bit about my thesis research over the last 3 years here at UAH under Dr. Kevin Nutt. The title of my thesis is Cold Season Severe Quasi-Linear Convective Season Events over Northern Alabama, Climatology, Cloud, and Boundary Layer Characteristics that we found within. And we're going to jump into a little intro first off. For a little introduction, the cold season is generally defined within the meteorological community as the months of November through March. But specifically for this period, we studied the November 15th through March 15th period, so the last 2 weeks of November through the first 2 weeks of March. And tornadogenesis in the southeastern United States often occurs under a broader range of conditions than expected in other regions of the country. And even in here, right here in North Alabama, throughout other seasons. So it's a very different time of year for tornadoes. High shear, locate, or HSLC tornado events pose major operational forecasting challenges. A lot of us operational forecasters really struggle with that environment and understanding exactly how to forecast tornadoes. And it is so, even violent tornadoes have occurred under these high shear locate tornado conditions. Some examples of which were February 6, 2008 and December 24th or Christmas Eve of 1988. And if you look down to the next to the bottom bullet, both quasi-linear convective systems and supercell convective modes have been observed under high shear locate conditions. The warm season events can happen in cool season. So you can have anomalies where you normally wouldn't expect to find certain types of tornadic activity or these high shear locate events. As conversely, you can have cool season-like events that occur in non-traditional months of the fall, late spring, etc. A little more introduction. Some research questions for this investigation, some of the things we wanted to answer, some of the questions include the following. What is the range of cloud-based heights associated with the clouds atop or within the boundary layer during the cold season, severe weather and tornado events? Number two, what is the stability class of the subcloud layer? So we wanted to look at something called cloud top mixed layers, and we wanted to analyze for the presence of those. And we found that in a lot of cases, those didn't exist in high shear locate tornado events. And so we therefore wanted to study the subcloud layer and the surface boundary layer stability. Is the subcloud layer coupled to the cloud layer? If it is fully coupled, if it's a fully coupled cloud top mixed layer, then the lapse rate should be adiabatic, and the subcloud layer turbulent, as we just mentioned. What are the characteristics of the wind profile within this subcloud, within this cloud top mixed layer, from the surface through the cloud layer and above? So we wanted to determine if the wind field was related to the stability class, and vice versa. How are these two interconnected? Some background and motivation. Parameterization of the convective boundary layer via local and non-local numerical weather prediction, NWP schemes. This was a study that was conducted by Cohen et al. In 2015. So they wanted to determine if the storm relative helicity and instability or boundary layer stability was different and how it differed between the local and non-local numerical weather prediction schemes. how cloud top mix layers were important and how that affected boundary layer stability and wind shear. Lifted condensation level, or LCL height, and its role in the high shear locate environment. This was a study that was conducted long ago by Rasmussen and Blanchard about 20 years back. Low-level thermodynamic characteristics in southeastern U.S. tornado events by Jackson and Brown from 2009. The differences between LCL height and observed cloud-based height. This was from Craven and others in 2002. And the importance of boundary layer relative humidity in tornado genesis. And as we know, this is a very important one. And this actually relates back to this bullet up here. We know that the stability and the relative humidity, the amount of water vapor within the boundary layer, affects the lifted condensation level height. Some methodology for you. We used a suite of in-house operational instruments to observe different parameters within the atmosphere for this study. One of which was the LiDAR ceilometer out here on the berm out here, also attached to our MIPS in-house tool, and the NOAA ASOS data set. So we had two different ceilometers that we drew data from to determine cloud-based height and cloud fraction. And the UAH data consisted of using the lowest of the 1 minute ceilometer observations binned in 5 minute averages. So basically what we did was there's 1 minute ceilometer observations. We took the 5 minute chunks, intervals, and we found the lowest of those 5 observations and used that as the point. And then bullet number 2, Doppler wind LiDAR, we used that to define the boundary layer wind profile. Microwave profiling radiometer, we use this for water vapor, that's the MPR again. We also use balloon sondes, radiosondes, weather balloons. Then current cases include most of the Southeast, Alabama, Mississippi, Louisiana, Georgia, and Tennessee. Also, we use the NCEI, National Center for Environmental Information's tornado database to determine tornado intensity, time, and location, path length, etc. So that's some of our methodology. And moving now into some results. Cold season tornadoes in the Southeast display a much broader range of temporal occurrence, so they can occur many times of the night and day. However, as we'll discuss here in a minute, there's a specific time in the evening and overnight hours that we've found that they are most common. Cloud-based heights tend to be less than 800 meters for both QLCSs and supercell events. We have found some categorical differences between the two, and often the QLCS examples overall have a little bit higher of a cloud base, but that's not always the case. There are some categorical differences. We'll discuss those. QLCS cases, again, have the highest observed cloud base. QLCS cases also had the highest storm relative helicity. And we determined this was more likely the case due to the lack of a cloud top mix layer. So stratocumulus clouds forming underneath the inversion. There was not an observed cloud top mix layer in many of these cases. However, what happens is boundary layer turbulence, boundary layer stability sets in or is in place, and therefore the turbulent mixing in the boundary layer goes to pretty much nothing or very limited. Therefore, the surface flow decreases and the bulk shear increases. And the wind profile is, there's more bulk shear within it. So in the vertical wind shear profile. Cloud cover tends to dominate southeastern cold season tornado days, hours in advance of tornado genesis. So we'll talk more about this in a moment, but typically for the QLCS cases or the squall line cases, we have found that stratocumulus clouds exist about 200 minutes on average, so a little over 3 hours prior to tornado genesis. Whereas the supercell, the individual cell cases, those tend to exist, the stratocumulus clouds, about 90 to 100 minutes before on average. The stability was observed to be common. Atmospheric stability, boundary layer stability, was observed to be common within the subcloud layer, as classical cloud top mix layers were not observed in most cases. Storm relative helicity there at the bottom was observed to increase, as we mentioned, during overnight hours due to reduced boundary layer turbulence. This was one of the primary results that we discovered when looking at these. A large part of these overnight cases had this, where the boundary layer was stable, an environment that many forecasters or research, just the meteorological community, would not consider favorable for tornado development, produced tornadoes. So that's interesting. Jumping into some figures here, this is a monthly distribution of cold season tornado days. So this is covering our period from the last 2 weeks of November through the first 2 weeks of March. And you can see that the maximum occurrence occurs, as we mentioned, from the last 2 weeks of November into the first part of March. And that was our climatological peak during the cold season. Cold season tornadic storm mode distribution. So what was this distribution of quasi-linear convective systems, squall lines, and supercells? We had 39 squall line cases, QLCSs, and 19 supercell cases.
Tim, are you on the line? I've got a call.
No problem.
Okay, back on the air. Sorry about that.
All right, so we had 39 QLCS cases, squall lines, and 19 supercell cases. We had noticed down here at the bottom, the 0, I was not able to find any other storm mode that was associated with QLCS with cold season tornadic convection, excuse me. And so in some of these cases really featured little to no lightning. I think 3 or 4 of the cases had no lightning whatsoever, which is fascinating to me. But no multi-cell convection or anything like that, just QLCSs and supercells. And the QLCS cases were 67% of these cases. By the way, I should mention, these cases are quantified or searched for within 120 kilometers only of the armor radar. Here's a bi-hourly period of the tornado distribution throughout our study. We found that it was best to bend the time periods into 2-hour periods. And using UTC time, Zulu time, we found that the peak tornado occurrence was between 2 to 11 UTC. And really 2 to 7 was the peak, and then a little slack off here, and then another local neighborhood peak there, 10 to 11 UTC. So that was interesting to observe. And again, we find that that's probably occurring due to increased boundary layer stability, reduced turbulence in the boundary layer, increasing the storm relative helicity, etc. We'll move more into that in a moment. Here's some measured or observed cloud-based heights in blue, the Mark Lawrence equation from 2005 in red, and I give that equation right here. It's elliptic condensation levels defined as 125 times the difference of temperature and dew point. And so the temperature and dew point is in Celsius degrees, and this indicates the lowest possible LCL level, given the 2-meter surface conditions. So if there's mixing in the environment, entrainment, et cetera, there may be a difference there as observed here. You can see the blue is the ASOS oscillometer results. The red is the Mark Lawrence equation estimate. And the green, the light green there, is the SPC meso-analysis data using their LCL height estimate. And what that uses is the lowest 100 millibar mixing ratio is ingested into the RAP model, and that therefore spits out some results. So that's that. And a couple of the interesting results you can see, especially for the QLCS cases, they're very similar. The null cases here are defined as days when there were tornado warnings, but no tornadoes actually occurred. That's what we define nulls as. And you can see that QLCSs and QLCS nulls are very similar, but take a look at the difference between the supercell and the supercell null case. That's a tremendous difference in LCL height or observed cloud base there. Probably owing mostly to mixing and a little bit more instability observed with many of those cases. Much of the same represented in box and whisker plot form. Again, using the same 50 cases as previously mentioned, just displayed a little bit differently. One interesting result here is you can see some of the extrema observed with the QLCS cases for the SPC meso. In supercell 2, I believe, but notice how extreme some of those outliers are. And that may have been cases where the NWP ingested the information wrong, or something in the boundary layer processes were off with either the non-local local scheme. So here's some more oscillometer observed information, bend into time periods. So we did these time periods to try to help further understand the cloud-based heights with time for the individual storm mode categories. And as you can see, the supercell result here for the daytime was vastly different than the overnight hours for the supercells in green. But the QLCS remains somewhat similar. A little bit more difference here in In the daytime period, our upper quartile there was distributed a little bit further up the chart, so a little bit more range on my cloud-based height during the afternoon. But really nothing much different than the 0 through 6Z through 12Z time period. This is storm mode ceilometer-based cloud fraction observations. So what we did is, again, we used those 5-minute chunks of data, and we looked at the 1 minute, each of the 5 individual 1-minute periods within that 5-minute chunk. And we said, within the ceilometer, there's 3 levels. You have a lower level, a mid, and an upper. How many of those 1-minute periods did we observe stratocumulus clouds within the lowest level of observation within the ceilometer? And this is the distribution for that for 50 cases. You can see within the supercell category here that we've got a much less amount of cloud fraction. Cloud fraction was lower, whereas QLCS's, you had much higher cloud fraction, averaging 96% for the QLCS cases in the time in the hours leading up to tornado genesis. But for supercells, much, much less. I think it was 83% average or mean, arithmetic mean for supercells. We wanted to compare the ASOS ceilometer data in blue, that's in red. UAH data from the berm, or MIPS, is in blue. We wanted to compare how do these 2 ceilometers respond, and how do they relate in their observations? Are they similar or not? And the difference was 50 meters on average for the same 10 cases, the same dates. We just wanted to see how they related. Very similar. The presence of stratocumulus cloud prior to tornado genesis, as I mentioned in the introduction, was 200 minutes for the QLCS cases, and for the supercell events, it was 90 minutes. So the stratocumulus clouds appeared much sooner to tornado formation time or tornado genesis with supercells as opposed to QLCSs. We relate that back to boundary layer stability, the inversion, as well as stronger advection in many QLCS cases. You have a very strong low-level jet that oftentimes precedes the passages of these lines, etc., for the differences. Here's cold season storm relative helicity. I should mention that we used this equation from Davies-Jones 1990 to compute storm relative helicity using Excel, and these are the results. Very interesting. As you can see, the QLCS cases right here dominated, had much higher storm relative helicity observed. This was using VAD wind profiles, VWP, and the QLCS cases won largely, and the supercells quite a bit less. However, the most interesting thing to note here is take a look at the power of discrimination in this box and whisker plot for the 0 through 500 meter layer. This not only allows you, here in a minute we'll also look at TOR versus no TOR. This is just discriminating supercell from QLCS. And you can see there's very little overlap in the inner quartiles for this 0 through 500 meter layer as opposed to the higher levels that we looked at. And so that 0 through 500 meter layer, as we suspected, was very interesting and useful. This is bulk shear using the same levels. Essentially, I think we went a little higher for the bulk shear, 0 through 6 kilometer, because storm relative helicity is typically only calculated to a maximum of 3,000 meters. So we wanted to go higher for the bulk shear because typically we can get storm formation, a storm mode and storm formation likelihood from 0 through 6 kilometer bulk shear. So we included that, and what we found was very interesting. So pretty much the same thing, except this right here, the supercell, again, very, very powerful discrimination, and the QLCS both. I was amazed at how strong that power of discrimination was. Very good for the 0 through 500 meter layer. This is a 10 meter wind plot using our berm station out here at UAH, our berm location. 25 tornado and 18 null cases. Wanted to throw those null cases in there to try to better understand the environment. And the results were interesting. So the supercell storm mode and supercell nulls were somewhat similar, but then the QLCS nulls right here, we had this backed wind down here. Well, excuse me, I'll get to that in a moment. But the wind was a lot more distributed over a larger area for the QLCS nulls, whereas for QLCSs it was a little bit tighter of a distribution there. But let me get to an interesting thing, the wind direction here in just a moment. Wind gusts, The QLCS null case showing quite a bit of turbulence, probably associated with that result. The supercell and supercell null cases, you can take a look at that as well. But moving on to the 10-meter wind direction, this is an interesting result, I think. The supercell null, QLCS null, notice how much more backed it was, the flow. So you have a wind much more out of the east-southeast or southeast as opposed to the supercell and QLCS tornado events. And we think that's possibly associated with wedge fronts, cold air damming events from the southern Appalachian Mountains could have a lot to do with that. We're going to take a look at a case study now. This is the 30 January 2013 QLCS tornado case. You have these transient little line segments in through here, maybe some mesocyclones, mesovortices. A particular one that caused a tornado in western Lincoln County, Tennessee, near Delrose at 1046 UTC, produced an EF1 tornado. So, and this is an image from Armor, taken directly from Armor, 0.7 degree PPI. One of the interesting things is most of the tornadoes are weak in the high shear low cave environment, and you can probably infer that from other things that have been discussed. But most of them are fairly weak, but not always. We have had strong and violent tornadoes in this environment, and it must be recognized accordingly. Here is the observed cloud base with the Lawrence estimate also superimposed onto it. The solometer observation from our UAH solometer is in blue. Our Lawrence equation estimate is in orange, and you can see I've marked the average minimum cloud base here in black dash, as well as the tornado genesis time here at 1046 in Lincoln County, Tennessee. And you can see that we maintain a fairly uniform cloud base, average minimum cloud base until the onset of precipitation, where mixing and things are occurring in the stratiform region behind the line, and the onset of rain marked in the vertical red dashed line. And the average, this case fits very well within our averages of our average cases, 676 meters for this particular case. Here is a plot using the microwave profiling radiometer data. The vertically integrated vapor is in blue, and the vertically integrated liquid water in orange. And you can see that they stay pretty steady state, remain pretty steady state until the water vapor increases dramatically right out ahead of the QLCS as it begins to move in. And also as stratocumulus cloud thickness increases, you can see this dramatic jump in both the vertically integrated vapor and vertically integrated liquid water. SubcloudLapse Rate. This was a derived product that we studied using the cloud-based infrared temperature from the NPR, the cloud-based solometer observed cloud base, as well as the 2-meter surface temperature from our berm site. And we were able to determine that the subcloud layer was sub-adiabatic and therefore indicating stability within the boundary layer. Average subcloud lapse rates were 5 to 6, 5 to 7, more like 5 to 6 Celsius degrees per kilometer, I should add. This is another parameter we looked at. This is the 9.5 meter temperature difference. And what we did was we wanted to observe the difference in temperature between the 10 meter observation and the 0.5 near surface temperature observation using our 10 meter tower out here on the berm, at the berm. And one of the interesting things that we found was typically there was an inversion or stable conditions. Conditions resembling an inversion where you had warmer temperatures, slightly warmer temperatures at 10 meters as opposed to the near surface 0.5 half meter temperature. And that was observed here. And then as the other plot, you can see the onset of rain here at around 1050 UTC. So stability is the key take-home message here. You're going to have a lot of stability with many of these high shear, low cape, cool season tornado days. So some conclusions for you. Stratification of the low cloud deck often results due to strong advection and boundary layer stability. Classical cloud top mix layers were not observed, leading to boundary layer stability and enhanced wind shear due to a reduction in surface or boundary layer turbulence. Low clouds prevailed for about 90 minutes prior to tornado genesis cases with our squall line cases, QLCSs, and about 200 minutes, that was 90 minutes for supercells, 200 minutes for squall lines during the cold season. Salometer observed cloud fraction was 97% for QLCSs, so the cloud coverage was a lot greater for squall line cases, and 83% for supercell storm modes, so a lot less, significantly less clouds for a period before the tornado supercell cases. Noted differences in kinematic parameters among storm mode and null cases. These were interesting. As we mentioned, the QLCSs had the greatest amount of shear, etc. And the importance of cloud climatology to numerical weather prediction validation down here at the bottom. So we want to be able to take this information, be able to provide it to others, to build a more robust data set and be able to understand the models better during these high shear locate tornado conditions. Some future work for you. We want to continue adding cases, additional Salometer cases to improve statistics. We want to increase cases for subcloud lapse rates and surface layer stability and understand that more. That was really the real key of this message, the crux of this study, was to understand the subcloud layer and whether or not how turbulent the boundary layer was in the surface layer portion of the boundary layer during high shear locate conditions. We want to study the mixed layer characteristics more via radiosondes or weather balloons and compare radioson and Salometer observations and see how those two relate. I want to give you some acknowledgments. I would like to thank my advisor, Dr. Kevin Knupp, for his wisdom and insight into this project and everything I've learned from him. Additional committee members, I want to thank Dr. Larry Carey and Dr. Tim Coleman. Supporting contributions from Kyle Pennington, Corey Amiot, David Howitzer, and Christina Leach. And funding is from the Northern Gulf Institute. I appreciate that, GRA. And here's my references. And thank you very much.
Take questions from the general audience.